Hello and welcome back to Chapter 20, or Chapter 21, Origins of Modern Astronomy. This is the final segment within this chapter, and we'll be talking about the movement of the Earth, the Moon, and we'll talk about some of the phenomena associated with the Moon, such as lunar and solar eclipses. And then I'll just wrap up a little bit with telescopes. I really think that telescopes are pretty interesting, and there are a number of astronomers out there who've given talks on how useful they are and the kinds of telescopes and images we can sort of apply to the current problems of understanding the cosmos. So just a quick review: rotation of the Earth. We're talking about counterclockwise rotation if we're looking at the North Pole, and about 1,000 miles per hour at the equator. But as you know, it gets to zero at the poles. The period of revolution is counterclockwise as well if we're viewing it from the North Pole, with a seasonal change, and I'll show you in a minute in the stars caused by basically the areas where it's night. We're facing different parts of the universe or different parts of the galaxy, really. And then precession, which affects how we look at the stars as well, which is that wobbly rotation. So we look at Polaris as the North Star today, but every 12,000 years we go through a period where we'll be looking at a different direction, and in about 6,000 years at something called Vega. Okay, so if we look at the Earth down here in this elliptical orbit, Earth on the left, Earth on the right, we're looking at an image on the right here showing us Orion, and that is the night sky, so it's one constellation. And as we move around to the other side of the sun, when we get to our halfway through our rotational period, our revolution here, we end up looking at a slightly different view of the night sky. And that's because this part of the Earth is illuminated or is dark, and it faces a different direction in the galaxy, and this one is also dark, and it faces a different direction in the galaxy. So we don't see the same parts of the night sky constantly throughout the year, although we do see quite a bit of overlap as we move through these shorter, or what we call minor axes in our rotation. Okay, the precession, which is this wobble up here on the right-hand side, right now we're facing with our rotational axis here is aligned with a star called Polaris. But as we come around in about 12,000 years or so, we'll make a full rotation, and we'll be aligned with Vega. Okay, actually I think it's 24,000 years for precession to happen. So I think it's actually 12,000 years to bring us around to Vega. I have to double check that. And so that kind of cycle is part of what we call a Milankovitch cycle, but it affects the seasons, and it affects where we see or what we see within the night sky to some degree. Our orbit also gets longer over the course of different periods, and our tilt will also change as well. So all three of those things affect the Earth's climate to some degree, and our position in the solar system can influence what we're looking at. Okay, the Moon moves around the Earth. It's only at 384,000 kilometers from the Earth, so not even one astronomical unit, right? Very small. It has a nearly circular orbit around the Earth, and it has a rotational period that is equal to its orbital period. That basically means, it's a little confusing. Remember, our rotation is rotation on the axis, so that's how, what's the day on the Moon, for instance? How long does it take the Moon to rotate around? And then the orbital period is the time it takes to get around the Earth. Okay, and because they're equal, that means that the Moon goes through one rotation every 29.5 days. So in 29.5 Earth days, the Moon goes through one of its own days. Okay, and it's actually moving a very short number of degrees here. It's moving about 13 degrees or so for every 1 day. So 1 day of rotation in the Earth. the moon's going to move about 13 degrees. And that has some effect on how we perceive its motion and is relevant for eclipses and different phases of the moon. In this case, you'll notice down here on the bottom diagram, here's the sun on the right. There's a line there, there's a line there, and there's a line there. And so here's the Earth. There's a shadow on the left for all of these features, and a shadow is not present on the right. What we see is that the half of the moon or half of the Earth is illuminated, and that the moon at different positions, if in this case it's a new moon, so it's between the Earth and the sun, is casting this shadow, this little triangular shaped shadow, and that the full moon is also doing this, and it's doing it at the first quarter and so on. But you can imagine that at some point in this orbital mess, that tip of that shadow is going to touch the Earth, and when that tip touches the Earth, it's going to create what's called a solar eclipse, right? So that's when the moon is blocking out the sun and creating a shadow right at the Earth's surface. And we'll talk about that in a little bit. Why doesn't a solar eclipse happen every 29.5 days? Well, that has to do with this thing we call declination. And if I just erase all of my green marks here, right? Sometimes the moon is just a little bit above the ecliptic plane, and sometimes it's just a little bit below the ecliptic plane because it's tilted as it's going around the Earth, and it's tilted by about 5.2 degrees. So that means that the only time we're really going to get that eclipse is when the Earth, the moon, and the sun are all aligned on the ecliptic plane, and then we'll get an eclipse. And so this gives you a sense of like why we don't see an eclipse, either a lunar eclipse or a solar eclipse, every 29 days or so. And that's because they're not as the Earth moves around the sun, the moon, the sun, and the Earth are not always aligned on that ecliptic plane because of the declination of the moon as it moves around the Earth. What we do see every 29.5 days, or one lunar month. Okay, month comes from that sense that it takes a moon that 29.5 days to go through its cycle, right? Are different phases. When the moon is between the Earth and the sun, we're in the new moon, and that means that we cannot see it very well because what we see from the Earth, if you're a person standing here on the Earth, is you see this dark shadow, right? You see the shadowed side of the moon. But as the moon moves around to different position, what we end up seeing here is some part of the light and some part of the dark half. So we always only see half of the moon. So position A, the Earth is rotating around, and so the moon is relatively still. It's only moving 13 degrees per every day that the Earth goes through a rotation. We see part of it is illuminated and part of it is dark, and that gives us the crescent shape. When it's illuminated on the right-hand side, okay, from our perspective on Earth, looking up, we're going to call that a waxing moon, a waxing crescent. Okay. At some point at B, if you were to look up, you would see that you've got half the moon visible, and of that half, 1/4 is dark and 1/4 is light. And so we're going to call that the first quarter within the month, okay, or the month. As the moon moves to this position, okay, what's going to happen is we're going to look up and we're going to cut that moon in half again, and we see most of the moon is illuminated, and we have a little sliver that's dark. That's called the gibbous phase, and it's waxing because the area that is illuminated is growing. Okay, so waxing indicates a growing illuminated area, and as we move to the final position, for the first half of the cycle, we get the full moon, so no shadow, right? So on the left-hand side, there's a full moon, there's the full moon, but you can see that's cut off and that's cut off on that side there. So these guys are representing sort of the full position, or images in the full position. Now, I told you that all of these phases in here, right, we're all going to be waxing, and we can look up at the moon, and you notice the side that is illuminated here is on the right. Okay, so that means that all of these are waning. Okay, that means the area that's illuminated is going to be getting smaller in here, and so that notice all of these are illuminated on the left side of the moon. So you should be able to identify whether the moon is waxing or waning based on which side of the moon is illuminated. So as we come over to position C, and then we come over, let's say, sort of past the full moon position, looking off at the moon, we can draw a line through here. We see that the moon went from full, and now it's getting a little less illuminated, so we're at the gibbous phase. Gibbous, means more than half of the moon is illuminated, but gibbous in a waning stage means that the moon's illumination is getting smaller. We're at the third quarter, cut it in half, and we have a quarter illuminated and a quarter of the moon that is dark. Again, we're seeing it illuminated on the left-hand side. Moving to the waning crescent phase, now we're seeing only a sliver of the moon. That's just out here on the bottom left-hand side of this diagram, and seeing most of it dark. And then finally it comes back around to the new moon position where it is essentially dark, and we do not see it. At least it looks a little bit darker. Okay, so those are the basic phases of the moon that we're going to see. There are periods of time when we can see the moon rise and we can see the moon set, which are sort of relevant. I need to clean this diagram up just a little bit for you so we can talk about that. And the way you figure this out, and we'll talk about it in a lecture a little bit more, is to think about your position on Earth and the kind of line of sight that you might have to the moon, right? So if I'm standing at position A, so think of this as a sort of a top-down situation, right? The Earth is rotating like this. The North Pole is here, and I'm going to stand at position A and look up. Okay. Notice I'll just draw. Here I am standing at position A. Notice the Earth is half illuminated, so that this is about 6 p.m., right? And this is about 6 a.m. It's not exactly when the sun rises and sets, but it works for right now, okay, to think about it. So that means that, if I'm at position A on the Earth, which is rotating, this is noon. And so that means that at noon, the sun is directly overhead, okay? When is the moon is directly overhead. When is the moon going to set for me, okay? So the moon's going to stay here, and I'm going to rotate on the Earth to this position, and I'm going to still be able to see the moon in its new state at 6 p.m. I won't see it very well, but it would still be in the sky in theory, right? At 6 p.m. though, I'm going to pass through this point, and I'm going to be on the other side of the moon, headed towards towards midnight, right? And so at midnight, then, if I'm here on the opposite side of the Earth than a new moon, can I see the moon? And the answer is no. I cannot look through the Earth. I have no direct line of sight to see the moon. So the question often comes up, can I see the moon during the day? Is the moon only up at night? And the answer is, of course, you can see the moon during the day, and that has to do with where it is within this kind of cycle. So let's say we're at the moon is at this position here. I'm going to draw on this again. It's at the first quarter position. Well, if it's right here on Earth, I'm standing and rotating. Let's say it's actually the morning for me, and so I'm standing over here at D. Right? Do I have direct line of sight to the first quarter moon? No, I don't have direct line of sight because I have to look through the Earth. I do have direct line of sight to the third quarter moon, and I can also see waning gibbous. I could see the full moon. Okay, could I see the waxing gibbous? No, because I can't look through the Earth. Could I see the waning crescent? Sure, I could see that. Could I see a full moon from this position? Sure, and I could see the waxing crescent. No, I cannot. So I cannot see that. I cannot see this, and I cannot see these three phases of the moon while I am going from night to day, so in the early morning hours. What can I see during the early morning hours of the moon? Well, potentially I could see get rid of some of this stuff. I could see, or the question really maybe will be, if the moon is in the first quarter phase, when do I first observe it? So can I see it at position D? No, because I cannot see through the Earth, right? I first am going to observe it when it's right on the horizon for me, okay? And that's going to be at position A. So that means at noon, the first quarter moon here is rising, okay? As I move through my day, when is the first quarter moon going to be directly overhead? Well, it's when I get to the light-dark boundary, so 6 p.m., let's say, okay? So when I get to 6 p.m., the moon is going to be directly overhead, and so that means it'll be highest when the sun is going down, which is off in this direction. Can I still see the moon at midnight when I'm at position C? The answer is yes. I would still have direct line of sight to see the moon, but it will be at its lowest position, so the moon would be going down at that position. And you can play around with this, and we'll do this more in lab. I don't want to go into it in too much more detail than I already have. Okay? So we can see the moon at different parts of the day based on how the Earth rotates, and certainly we can see the moon during the day as well. There are some interesting features of the moon that you commonly see a really orange moon, and that has to do with how light's refracted through the Earth's atmosphere. When the moon is low, it turns out along the horizon, it turns out it's actually sending light, which is reflected off of its surface, through a thicker layer of atmosphere than when it is, let's say, overhead. So out here, this is thick, and up here, it's sending it directly through the atmospheric layer. It's sending the light through that. So this is thin, and what that ends up doing is it bends the light. It refracts the light a little bit differently, so that when it goes through the thicker atmosphere, we get more of the red light from the moon and less of the other colors like blue and green. And so more red gives it that red hue. So that's a real effect, right? But it's an atmospheric effect based on the position of the moon in the sky. So in that's true, then as the moon rises through the night, it should actually become a slightly lighter color, right? A yellow color or a white color. The other thing that you notice is that when the moon is at the horizon, it can look huge, right? It can be looking sort of massive. That is not real, okay? That's an illusion, and it has to do with how we perceive things at scale. So when you think the moon has actually changed size, the easiest thing to do is to take some pictures of the moon at different positions in the night sky and actually measure those pictures, and you'll find that the moon is not any bigger or smaller when it's at the horizon versus when it's up here high in the sky, directly overhead. So that the change in size of the moon is an illusion, but the color of the moon is not an illusion. That has to do with how light moves through our atmosphere. All right, so moving on to solar and lunar eclipses, I just want to talk a little bit about how their relationships between the Earth, the Moon, and the Sun. We'll talk a little bit about the most recent eclipse that happened in August of 2017 and the one to come. And then I'll talk about these different features. This particular term I introduced in the first week of class, where I asked you what a penumbra was, and I guess I actually told you so. Maybe you'll remember. Okay, what causes a solar eclipse? Well, what we need is to have the moon in front of the sun, and so that the moon is between the sun and the Earth. The moon is actually so far away, the sun is so small because we're at 149 million kilometers, that the moon is sort of able to block out the sun, just fit over it at the right location at the right time when the moon, the sun, and the Earth are all aligned along the plane of the ecliptic. Sometimes in moon's orbit it would sit up here and it would cast a shadow that wouldn't touch the moon. Sometimes in its orbit, it sits down here and casts a shadow. But when it's just perfectly aligned, as it's moving through the system along the ecliptic plane, it casts a shadow on the Earth, and you actually get two sort of perspectives on this shadow. The tiny shadow here, the little one, is called the umbra. Okay, so the little one is called the umbra, and that would be, if you experienced the last eclipse, that would be where the sun is totally blocked. And so down here on the bottom here, this is what the sun looks like when it's totally blocked. Right, the moon is large enough, just the right size, to sit in front of the sun because the sun's so far away, and we end up with a corona. That's the part of the sun's atmosphere that actually extends to a radius that's greater than the diameter of the sun itself. But that's the corona, so it's part of the sun's atmosphere that we're actually seeing, and we actually only see the corona when the photosphere, that's the surface of the sun, is blocked out, right? So here's the different phases. And so this is taken with just by the way, never look at the eclipse through anything. You should always use a kind of, sunglasses are not acceptable. You need a very, very dark protective film over a telescope, over a camera, and over your glasses. Anyway, that's my brief safety warning. As the moon moves in front of the sun, it's going to start to block it out. And, in Illinois, we got to probably around here, where we got about 80 or 90% of the sun blocked. So we had a slight shadow. There was a dimming of the light, but it's still pretty light outside. It's only at these places here where you get a very, very intense shadow. So you don't lose all the light, but you get a very dark shadow. And so the closest place to us, I think, in 2017 was like down in Carbondale, right in the southern tip of Illinois. And I have a map to show you that in the next slide. But let's see. Yeah, so here we are in Chicago. Okay, here's our phases. So we're really interested in this part where it gets totally dark. And that dark path is very small. It's just this path right here. So just a very small select group of people are going to get to see that full coverage. And then, down here, if you're in Mexico, you're looking at 40 to 60% of the sun is blocked out. If you're in Canada, it's 40, that's 60, and there's 50 there, 50, 40. And as you get down into the lower 48, here where we're close to Chicago, right here, we're getting close to 90%. So we got a little less than 90% of coverage, but it's only along this band that we got 100% coverage. Basically the moon blocking the sun, and we're going to expect to see another one cut across here in 2024. So not too long from now, maybe 6 years from now, we're going to see another total blockage. What's interesting is it took almost more than 100 years, about 100 years actually, for one to cross North America like this. Now, eclipses are happening all the time. The problem is that they're out, in the ocean out here or down in Tahiti. So you're just not always in the right spot to view them conveniently. Okay. Now, we can also get a lunar eclipse, and a lunar eclipse is when the Earth sits in front of the sun and blocks light headed to the moon. Okay, so that basically means we're putting the moon into shadow. And so here's our umbra of the Earth, right? It's our pointy shadow. Here's the moon. It's completely in shadow. And then here's the penumbra, which is a lot bigger on the Earth. Okay, but typically the moon doesn't go fully dark. Actually, what it does is it creates something called the blood moon. Okay, the blood moon is really the eclipse of the moon, and the blood moon is called the blood moon because it's red. Okay, why is the blood moon red? Well, it has to do with how light passes through the Earth's atmosphere. So the Earth has a diameter that's about 12,000 kilometers. Okay, and the Earth's atmosphere extends for another 10. So the Earth's atmosphere is way out here, right? And it even goes farther, like trace gases and little bits of gas and oxygen molecules and stuff are way out into space, okay? So that means that all of the sun's light actually is going to pass through the atmosphere here, and it's going to be refracted and bent. And so red light is going to be bent a little bit more, and that is what's going to reach the moon. So you can still see the moon during a lunar eclipse because light passes through Earth's atmosphere and is refracted and bent to illuminate it. And it looks red because that's the light that's bent sort of the most and actually reaches the moon. And that's based on physics and the refractive index of Earth's atmosphere at different elevations above the Earth's surface. So not something we need to get into too deeply. Okay. I wanted to wrap up talking a little bit about telescopes. There's a lot of interesting stuff to see, and I just wanted to bring to your attention kind of the electromagnetic spectrum. We haven't talked about this in a little bit, but really everything, including electrical current, sits on a spectrum, a wave spectrum. Electrical current is way out here. It's a very long wave kind of radiation, so it's sort of low energy, not very dangerous, and then way over here we have our gamma rays, stuff coming from space, very short wavelength and high frequency waves, and tend to be fairly damaging and dangerous. And then all we see with our naked eye is this. So if you go back to, let's say, the 12th century, all you were able to see was, this part of the spectrum, 15th, 16th, 17th century, 18th century. You're still really just looking at this part of spectrum in space. And it's not until we started looking for other parts of the spectrum did we see or begin to see all the picture, right? And so the idea here is that we have a very limited picture of what's going on out in space. Is there stuff to see that emits gamma rays? Absolutely. Is there stuff to see that emits X-rays? In fact, black holes emit X-rays. Yeah, so in a sense, if we don't look at the entire spectrum, both the long wavelength and the short wavelength parts of the spectrum, most of what we see is limited to this little visible area, and we're kind of blind, okay? So, here's how a refracting telescope, a basic one, works. Light is going to enter into this objective lens, which is here, and it's going to be bent as it passes through this objective lens, and it's going to be bent to a focal point. Okay? It passes through the focal point, and then we use an eyepiece to magnify the image. So the image that we see is actually this thing right here, right? And then we actually look at the image at the focal point using this eyepiece to magnify whatever it is that we're looking at. Now, most of the time we got to look at stuff out in space because it's not very bright at night and it's not emitting very much light. If we want to see far, we need to get more light into our object, and so we need a bigger lens, right? A bigger lens means a larger surface area, and that means more light, and so things will be clearer and things will be brighter if we have that. However, if we keep extending this thing, what we find is that we get distortion. And what happens when you have a very big lens like this is that as the light comes in, it comes in as white light, okay? But the refractive index of the lens bends the light at different angles. So as it exits, some light gets bent into different colors. In other words, the spectrum begins to separate. Okay, and what happens then? We have a lot of different ray paths of, red, orange, yellow. Here, red, orange, yellow, right? These different ray paths. And do they all meet at one focal point, which is what we need, right? The focal point. The answer is no. They don't meet at the focal point. And so what does that result for us? Well, it results in something like this on the left-hand side, which is poor resolution, right? So we can see into space, but it looks pretty blurry. And so that has to do with the fact that a refracting telescope, a telescope that bends light as it enters, begins to distort light at a certain size. Now, you don't have to get very big before this starts to happen. And so one way around this is to do something else, which we started to see with Newton, which was to make a reflecting light telescope. The reflecting telescope, we need a big lens, right? We need something that is quite large here to collect as much light as possible. But we can collect a much larger lens, and because we're not, and we can make it parabolic, curved, so that it bounces all the light to a particular focal point here. And then we can, again, we're looking at the focal point from our little eyepiece over here and magnifying it. But reflection does not distort the light as much as refraction does. Okay? And so that's what makes the reflecting light telescope allows us to see farther out into space because we can collect more light without distorting the image. Now, what happens when we start creating bigger and bigger mirrors? Well, if you're interested in engineering at all, you know that you can't just scale something up to some ginormous, huge size and expect it to behave in a regular fashion. The bigger the object, it begins to distort, begins to develop imperfections, and we lose the resolution because we don't get a tight meeting of all those ray paths that have come into the telescope and then bounced off of the mirror. And so we get, again, back to something like this where we don't get good focus on our telescope. So how do we get around the issue of basically an object starting to sag beneath its own weight? Well, one of those examples is the Keck telescopes. The Keck telescopes are housed in these two observatories here. And instead of one large reflecting mirror, they're made of multiple mirrors that give a total diameter of about 10 meters. Okay, so each telescope now has a 10 meter diameter mirror. This is much bigger than you could, grind out with one piece of glass. And so, or whatever the material might be, if it's metal, that's fine too, before it begins to distort. So we use many, many mirrors that are all working together to create a focal point. And then what we also did with the Keck experiment here is we set up two telescopes side by side, separated by a distance, just like eyes, right? So they're separated by some distance here. And so they actually create a parallax, but they can both be focused on the same object. And this actually increases resolution. Just like our eyes are seeing in stereo, we're going to be able to see greater distances with better resolution from the Earth's surface, right? So that's what separating those telescopes allows us to do. Now, what's the ultimate problem with putting a telescope that only looks at the visible spectrum on the Earth's surface? Well, the atmosphere is full of dust, and the light that comes in to the atmosphere is distorted already as it moves through the atmosphere to the Earth's surface. So we're already, just by looking at stuff from the Earth's surface, we're handicapping ourselves, right? So what's the next thing to do? Let's put something into space. And so the Hubble Space Telescope became famous for a number of reasons. One, because it takes amazing pictures that almost are just too hard to imagine what you're looking at. So here it is at the top left-hand side of the screen. But it takes just phenomenal pictures. It's well beyond its shelf life. So most of the time NASA puts together these projects, or JAXA, which is the Japanese Space Agency. They're supposed to last just a couple of years or 10 years, and they go on for 20 years or 30 years. So Hubble's still out there taking images, as far as I know. The image on the right is what's called a deep space or deep probe image. And what they did is they took the telescope and they focused it on an area of space that's about as big as your thumbnail. So if you hold your arm out and hold it up to the sky and look at your thumbnail, the image on the right that I've blown up, that image could fit on your thumbnail. This is what Hubble saw. And it took 10 days. So it just sat there for 10 days collecting information on this area of space. And this image is what came out of it. And it is fantastic. These are all galaxies that we cannot see this stuff from in any kind of resolution. Like, that's a galaxy. All these things that you're seeing, different galaxies. And I mean, it just gives you a different perspective on essentially the universe being much more heavily populated. I mean, space is big, these distances are big, but when you look in the night sky, you just have no perception of this stuff. It also gives us better resolution on things like stuff that we already knew was out there as well. And so if we move outside of the atmosphere, we lose that distortion. Now, the Hubble is still doing or working in the visible light spectrum. Okay, if we want to put a telescope out in space that looks at X-rays, we can do that. We cannot look at X-rays on the Earth's surface because the Earth's atmosphere blocks X-rays, which is both a good thing and a bad thing. I guess if you're an astronomer, it's a bad thing, and if you're a person, it's a good thing just for life in general. But if we wanted to put and there is a plan to put an X-ray telescope out there in space and to look for X-rays. But on Earth, we can also go to the other end of the spectrum to go from very short, which is X-rays, to very long wavelength. And that's what radio telescopes really do, is that they actually have a couple advantages. They can see great distances, right? We can make telescopes by either making giant dishes. So here's Arecibo. You probably saw this in one of your it's not too old. That was like in the 90s. The film, one of the James Bond films. He's actually at Arecibo. And there's a collection of, radio waves come in and are bounced up to a receiver up here. But we can also use radio waves that come into the dish and get bounced up to the receiver. And we can use them in arrays. So this is the very large array in New Mexico. There are huge telescopes that are put together over like 10 kilometers. Very simple devices that are collecting these radio waves. There was an experiment that's going on in Australia where they have these massive telescopes collecting radio waves. There's no difference really between radio waves and light waves except for the wavelength. And so we can see different things. Radio waves are not affected by dust, but they are affected by all the radio noise. So you have to go to a radio quiet area, which, the deserts of Australia, the deserts of New Mexico would have fewer radio waves, like ambient radio waves passing through the area, and to sort of point them at different objects to see what kinds of information come in. So we're looking at putting things out in space that can look at X-rays. We're putting the Hubble, which is still operating out in space, looking at visible light, and then we're coming all the way over to the long wavelength part of the spectrum to see out into deep space and to see, sort of through our atmosphere with greater clarity. So you get different improved resolution, greater distances, and different objects or different kinds of things are going to be visible depending on what the kinds of wavelengths that they're emitting. All right, so that's basically it for chapter 21.